Okay, it's time for another episode of Let's Tear Our Hair Out with Asteroid Commander. And I've got the sun and stars working. It's the sun now appears behind the asteroid, and when you see sunrise over on the right hand side of the screen here, you'll see the sun peeking out first, and then the terrain will light up. Let's just go fast forward. So now it actually looks like the asteroid is being lit up by the sun, which is nice. And of course, the star field looks a lot better. I got rid of all of the nebulas that I had been using to represent the Milky Way. They just cluttered it all up. And this is, here we can watch the sun going behind it again. Now, this is a lot more apparent how much better the star field looks when we go zoom out. Just added this yesterday, and this was actually really easy to add. The same tiles that the asteroid was displayed on before, they're still there, except most of them are just black except for the 4 tiles in the center, and I've done a new ray tracing on those 4 tiles. So it's mostly the same subroutines showing this asteroid, just a couple of different lookup tables for what it is that you're seeing, and you can click on spots on this asteroid still and move around it, and of course everything changes. And let's just go down a little ways to 40 degrees south, and you can see that it's not just sweeping the stars from left to right across the sky. It's actually they're moving in circles. And we'll go like this. Let's go a little further down. And if we go right to the South Pole, you can see them just moving in a circle around the asteroid. So everything works for the stars. I'm very, very happy with that. I'm really happy with the fact that it's now possible to see recognizable constellations. Let's just go to 32 North here, and pretty soon we'll see Betelgeuse coming around. It's the only really bright red star I've got. And there it is. And there's the Belt of Orion, and yeah, sometimes bright stars will appear in different spots. I do have a couple little bugs. I see Betelgeuse bouncing around all over the place. And not quite sure why that's happening, but yeah, got recognizable constellations. If we go further up, further south rather, let's just go to about 58 south here, and if you kind of squint, you can see Andromeda, you can see Perseus, you can see Draconis, and yeah, there are recognizable constellations. So that's really nice. Now, how did I do this? Well, I'm going to just touch on it lightly here. I'm going to go into a lot more detail in the Commander X16 forums, but I'll bring up this paint here. So imagine that the large black circle is a sphere of unit radius, and O in the center, that's our origin at 0, 0, 0. And our view center is at V. And the circle around V is the limits of our view. It's 30 degrees from V is the circle, that blue and purple circle. P is a point on that gray line. That gray line is a curve that's passing through our viewpoint as the star field rotates around the asteroid. W is a normal vector to V. It's at 90 degrees to it. Both V and W have x coordinates of 0, so only the y and z values change. U is also a normal vector. It's also perpendicular to both V and W, and it has the property that its y and z values are the same as V, but its x value is -1 instead of 0. So U minus V is just -1, 0, 0. And W minus V is 0, and then WY minus VY, WZ minus VZ. So when we are looking at this screen, the screen can be rotated. So we have to convert our position of our star, first of all, into Cartesian coordinates to determine the radius r, and also the angle that it makes uh, with w, which is theta. Now, to determine r, you see in the bottom left there, it's just the Pythagorean theorem, and delta x squared is just px minus vx, and since vx is 0, that just becomes px squared. Delta y squared is py minus vy, and that is a constant for this particular view and that particular declination. And so that's just saved in a lookup table, that delta y squared. And the delta z squared is pz minus vz. Now vz is known for a particular view. There's only 21 different latitudes in this game, so each one's got a view z that's recorded in a lookup table. And so you have to calculate pz first of all, and then subtract vz, square it, and then add it to those other square values, and then take the square root of that to get your radius. Now, square root is a fairly expensive computationally expensive function, and when we're looking for that theta value, we have to do a division. It's the dot product of p with either the vector u or w, and that dot product divided by the radius, so we've got a division, and then you've got to take the arccosine of that to determine theta. And arccosine, when our values of that quotient are of dot product over r, when those values are close to plus or minus 1, your arccosine value gets less and less accurate. So what I've done is I have two different arccosines that I could possibly use. One of them is if your theta is within 45 to 135 degrees of w, then you use the dot product p minus v and dot w minus v. And if not, then it's within 35 to 100 or 45 to 135 degrees of u, and so you use u minus v dot p minus v. Now, because u minus v is 1 or minus 1, 0, 0, that dot product just becomes minus px, and the quotient is just minus px over r. So we've got a quotient, we've got an arccosine, we've got a square root, we've got square function, and all of these are computationally expensive. And how do we do that on an 8-bit computer fast enough to display up to 80 stars? The way we do that is lookup tables. So if I go to my mult function, we can see that this multiplies the value in the accumulator by the value in the wide register. And these values represent the range minus 127 over 127 to plus 127 over 127. So minus 1 to plus 1. So when you multiply them together, you get a value that's also in the range of minus 1 to plus 1. So this multiplication routine just looks at each bit that was in your multiplier, and if it's present, it looks up a value in a table according to the multiplicand and adds that value to your running total. So this multiplication routine, in worst case scenario, when the accumulator starts with FF, the total time is 103 cycles for this subroutine. In the average case, where the accumulator has 4 bits on and 4 bits off, it takes 80 cycles. So this is a very, very fast multiplication routine for multiplying two values between minus 1 and plus 1. But it relies on 2 kilobytes worth of lookup tables. If we go to SQAL, this is another lookup table it's the low byte of a square function, and the square function is not just n squared, it's actually 65,535 n squared over 65 squared. That way you can have values between 0 and 65 will produce a 2-byte value between 0000 and FFFF. So 65 produces FF, and for the high byte, also FF. And this is because our radius is never going to exceed 65 and still be visible. It's actually only going to be 64 and still be visible for stars, but the sun is a slightly larger sprite, and so it will be partially visible when the radius is 65. So this way our squares will fill up the possible range from 0 to FF, and when we go to our square root table, then it just takes the most significant bit of the low byte of the square, and if that's high, it rounds up the high byte, and then it uses the high byte as an index into this table. So this one will return a value between 0 and 65 if the high byte is rounded up. High byte is 00 to FF. So I've taken the square root function, which is computationally intensive for an 8-bit computer, and just gotten rid of it altogether and used lookup tables. Same thing for division and arccosine. Rather than calculating out each of those to get our theta value, there's only 64 possible radii, and in fact only 56 possible radii, just the values between 7 and 65. I guess that's 57 possible radii. 59. My math is off. Whatever. So yeah, you've got the dot product is a single byte. You've got an integer for the radius, and there's only, fewer than 64 possible ones. So rather than trying to calculate that out on the fly, what we do is we have two banks of banked RAM that are set aside for the arccosine function. And the numerator is actually a scaled numerator. The numerator has been multiplied by 127 over 65 to take up the maximum possible range of this table. And so you see only values between 40 and C0 here. This table here, ACO1, this is just the start, the first of 32 in this bank. And so the numerator is just your y-index, the denominator is just which page and in which bank. And so that gives you a value between 40 and C0, which is actually one bit more than we need to produce our theta value. So another thing I've got going on here is for sine and cosine. I don't just have one sine table and one cosine table. I have 4 of them. And I've divided up the circle into 256 parts. So you can, I call them bigrees because they're binary degrees, and why not? So these two tables overlap because the sine and cosine functions overlap in the exact same way. And so this one is for exact values of bigrees. But if we go further down here, there's a couple other tables wedged in between. This sine 1 table is for an offset of 1/3 of a bigree. We go further down and we got a sine 2 table. This is offset 2/3 of a bigree. So I could, using sine 0, sine 1, and sine 2, I can divide up a circle into 768 parts. And going further down, there's also a sine 3 table. This one is for offset 1/2 of a bigree. So I can also divide a circle up into 512 parts. So using these four sine and cosine tables, we can divide a circle up into 256, 512, or 768 different angles. So when I am doing my arccosine function, and it's returning this value between 40 and C0, I just shift that right one bit, and now it's a value between 20 and 60, which corresponds to our angles of 40 to 135 degrees. And that extra bit determines whether you use sine 0 or sine 3, whether you use the exact bigree or offset by 1/2 bigree tables. Now, these only give the values between 45 and 135 degrees, and plus or minus. So we go back to our little diagram here. You'll note that if the angle made by P with respect to W is outside that range of 45 to 135 degrees, then with respect to U, it is within the range of 45 to 135 degrees. So we can use the second cosine theta minus pi over 2 equals, well, it's minus px over r. So if we get a failure, if we get FF when we look up this table using the first dot product, we can just simply change our y, or change our offset to minus px and look up in the same table again, same radius, and find a value that we then just add 40. Add 40 to it, which is 90 degrees, and we get our original theta value. And there's a little more complicated than that, because arccosine is a mirror image function, so you have to know which side of it is, and whether multiply by plus or minus 1. But I'll go into more detail on that in the forums, in the Commander X16 forums. But for now, I got my stars working, and I got my zoom out working, and yeah, it looks like you're really looking at something in space now. And because I've got the zoom out and all this background stars working now, I can also start having ships orbiting the asteroid. I'm thinking as many as 6 ships. So in the zoom out view, all of your ships will be visible no matter what direction you're looking at it. You'll see them all orbiting the asteroid like so. And they'll be orbiting much slower than, well, they're moving around here at a different rate than the stars themselves. I haven't quite done all the math on that yet, but you'll be able to see all of your ships in orbit and be able to have different types of ships, like cargo ships or space solar power satellite, or maybe a big laser defensive weapon or something like that. And yeah, it's I'm pretty happy with it. I've got recognizable constellations, and it's very fast. So I'm pretty happy with the way this has turned out. And so I'm on to my next thing, which is probably going to be the news feed at the bottom. But until then, have fun, Merry Christmas, and we'll see you next time.